If you recall, each chlorine atom has 7 electrons in its outer shell or its valence shell. Therefore, in order to form a covalent bond, what they will do is that each chlorine atom will share one of its valence electrons, overlap its molecular orbitals, and form what we call a covalent bond. So each chlorine atom will both give up one of its electrons to sharing, and as a result will form a covalent chlorine bond, which we usually indicate by a line. Now remember, whenever you see this line, each line indicates that that's one electron pair, where each chlorine had donated one electron to form the bond. Now, we call this an electron pair. I want you to realize that most times you will not see the two electrons separate. You will instead only see a line, and you will have to remember that that line represents an electron pair. Here I have shown the electrons in this chlorine atom as dots, while in this one I've shown them as X's. But in reality, electrons all look the same. But for clarity, I've just shown them using different symbols. Now, let's look at our chlorine bond that we have formed. This chlorine bond can also break. And when it breaks, there are two ways in which it can break. We can break it in what we call a homolytic manner. So you may hear your teacher say a homolytic cleavage or a homolytic fission. Basically, a homolytic breaking of the chlorine molecule. You can also have what we call a heterolytic cleavage or heterolytic breaking of the bond. So what do we mean by heterolytic and homolytic cleavage? Let's break down the word. Homolytic, homo means same. Hetero means different. So what this has to do is that when you start to break your chlorine bond, what you're going to find out is that the two chlorine atoms, if it undergoes homolytic cleavage, the same thing will happen to both chlorine atoms, while for heterolytic cleavage, different things will happen to each chlorine atoms. So what we do in chemistry is use arrows to show how the electrons are moving, because when the bond breaks, the electrons are actually going to move. In order to show the bond breaking, whether it's homolytic cleavage or heterolytic cleavage, we will have to show what happens to the electrons when these bonds break. So we use in chemistry a system where we use arrows to represent the movement of electrons. There are two types of arrows that we use. We use what we call curly arrows, or some people call them half arrows. Your teacher may give them another name. But let me move this over so you can see the whole thing. But your curly arrows or your half arrows will show the movement of only one electron. Please remember that only one electron is being moved when you use a half arrow or a curly arrow. And we usually indicate it like this, right? Just a simple arrow with only one of the top parts showing, right? The second way we use arrows is just a regular arrow, and this regular arrow shows the movement of an electron pair. Please remember, an electron pair is 2 electrons. So, if your electron pair is 2 electrons, we will show it using an arrow like this. And that's what we're going to be using now to show the movement of electrons. Please recall, if you want to show the movement of only one electron, you're going to use a half arrow or a curly arrow. And if you want to show the movement of two electrons or an electron pair, you're going to use a regular arrow. So now that we know how to use our arrows, let us look at homolytic cleavage and what would happen if this bond breaks. In homolytic cleavage, remember homo meaning same, the same thing is going to happen to the chlorine atoms. What this means is that when the electrons move, which we're going to use by the showing of arrows, each chlorine atom will gain only one electron. Basically, each chlorine atom is going to get back the electron it had started with. So we can use a half arrow to show that this electron will go back to that chlorine atom, while this electron will go to the other chlorine atom. So in other words, the electrons are going to move away, and what they will do is they will move to either of the chlorine atoms, because the same thing is happening to each chlorine atom, where each chlorine atom is receiving the same amount of electrons. We call it homolytic cleavage, or in other words, the breaking of the bond has been brought about by the separation of the bond in such a way that each chlorine atom gets one electron. So what do we get from that? What you will end up with is two chlorine atoms where they had their, remember now, each chlorine atom had 6 electrons to begin with, and then it got back the electron that it had originally given to the bond. So now what we have is a chlorine atom back in its unbonded state, right? The other chlorine atom, same thing happens. It originally had 7 electrons. It had given up 1 for bonding, but now through the breaking of this bond, it got back the electron that was involved in the bond. So let me just indicate here which of the electrons were involved in bonding. So what we end up with are neutral chlorine atoms. But because these atoms are, if you look at the atoms, what do you notice? They still want to be bonded. So they're very, very, very reactive. And so because of that, we call them radicals. So whenever you have homolytic cleavage, you are always going to yield radicals or neutral atoms with an unbonded electron, as shown here, or an unpaired electron, to be more specific. But what about heterolytic cleavage? Because the term hetero means different, obviously it means that what is happening to each chlorine atom is going to be different. So what the hetero refers to is that your electron pair, or your 2 electrons, will be moving together. What happens is that one electron pair, one chlorine in the bond, will receive the 2 electrons while the other chlorine will not. That's what we mean by different. So this pair of electrons will move, and remember we said when an electron pair is moving, you show it using a regular arrow. So let's say, for example, this chlorine gets the 2 electrons. It means that this chlorine didn't get any. But let's now look back at what the chlorines looked like before they were bonded. Remember, this chlorine originally had 7 electrons, but it had given up 1 for bonding, while this chlorine also had 7 electrons, 1, 2, 3, 4, 5, 6, and that 7th one which it had donated for bonding. So if it breaks in a heterolytic manner, what will happen? Let's look at this first chlorine with the electrons represented as X's. When the bond breaks, it leaves, but it leaves without the 7th electron. So this chlorine now will have 6 electrons. Wow. It means it has 1 less electron than it had started with. When it was 7 electrons, it was neutral. Now it has 1 less electron. So that means it must have a positive charge. It has 1 less electron than it had started with. The chlorine that has received the electron pair will now have, let me scoot over so you can see, will now have the 6 electrons that it originally had in the bond. It now got back the electron it donated along with the electron from the other chlorine atom. So this chlorine has the original 7 electrons, 1, 2, 3, 4, 5, 6, 7, and it now got an extra electron. So it has 1 more electron than it originally had when it was neutral. As a result, this chlorine will have a negative charge. So what you realize is that during heterolytic cleavage, you are always going to end up with ions. You'll end up with a cation, which is a positively charged ion, and an anion, which is a negatively charged ion. So during heterolytic cleavage, ions are always formed. Compare that to homolytic cleavage, in which radicals or neutral atoms were formed as a result of the breaking of the bond.